Well, this is Eric Michael Lloyd, master's have a master's in psychology, neuropsychology concentration. Uh, I'm continuing the reading on Beam Me Up and Einstein by Lauren Krauss, Wired.com, published in 1995. So this is 25 years ago. I left off at when a body has no body. Perhaps the most fascinating question about beaming, one that is usually not even addressed, is what comprises a human being? Are we merely the sum of all of our atoms? More precisely, if I were to recreate each atom in your body in precisely the same chemical state of excitation as your atoms are in this moment, would I produce a functionally identical person who has exactly all your memories, hopes, dreams, spirit? There is every reason to expect that this would be the case, but it is worth noting that it flies in the face of a great deal of spiritual belief about the existence of a soul that is somehow distinct from one's body. What happens after you die, after all? Don't many religions hold that the soul can exist after death? What then happens to the soul during the transport process? In this sense, the transporter would be a wonderful experiment in spirituality. If a person were beamed aboard the Enterprise and remained intact and observably unchanged, it would provide dramatic evidence that a human being is no more than the sum of his or her parts, and the demonstration would directly confront a wealth of spiritual beliefs. For obvious reasons, this issue is studiously avoided in Star Trek. However, in spite of the purely physical nature of the dematerialization and transport process, the notion that some nebulous life force exists beyond the confines of the body is a constant theme in the series. The entire premise of the second and third Star Trek movies, The Wrath of Khan, The Search for Spock, is that Spock at least has a katra, a living spirit, which can exist apart from the body. More recently, in the Voyager series episode Cathexis, the neutral energy, akin to a the neural energy, akin to a life force of Chakotay, is removed and wanders around the ship from person to person in an effort to get back home. I don't think you can have it both ways. Either the soul, the katra, the life force, or whatever you want to call it, is part of the body and we are no more than our material being, or it isn't. In an effort not to offend religious sensibilities, even a Vulcan's, I will remain neutral in this debate. Nevertheless, I thought it worth pointing out before we forge ahead that even the basic premise of the transporter, that the atoms and the bits are all there is, should not be taken lightly. The problem with bits. Many of the problems I will soon discuss could be avoided if one were to give up the requirement of transporting the atoms along with the information. After all, anyone with access to the internet knows how easy it is to transport a data stream containing, say, the detailed plans for a new car, along with photographs. Moving the actual car around, however, is nowhere near as easy. Nevertheless, two rather formidable problems arise even in transporting the bits. The first is a familiar quadry, faced, for example, by the last people to see Jimmy Hoffa alive. How are we supposed to dispose of the body? If just the information is to be transported, then the atoms at the point of origin must be dispensed with a new set collected at the reception point. This problem is quite severe. If you want to zap 1,028 atoms, you have quite a challenge on your hands. Say, for example, that you simply want to turn all this material into pure energy. How much energy would result? Well, Einstein's formula, E equals mc squared, tells us the suddenly transformed 50 kilograms, a light adult, of material into energy. One would release the energy equivalent of somewhere in excess of 1,001 megaton hydrogen bombs. E is equal to m squared. That's energy is equal to mass times the speed of light squared. It is hard to imagine how to do this in an environmentally friendly fashion. There is, of course, another problem with this procedure. If it is possible, then replicating people would be trivial. Indeed, it would be much easier than transporting them, since the destruction of the original subject would then not be necessary. Replication of inanimate objects in this manner is something one can live with, and indeed, the crew members aboard starships do seem to live with this. However, replicating living human beings would certainly be cause for trouble. A la Riker in Second Chances. Indeed, if recombinant DNA research today has raised a host of ethical issues, the mind boggles at those that would be raised if complete individuals, including memory and personality, could be replicated at will. People would be like computer programs or drafts of a book kept on disk. If one of them gets damaged or has a bug, you can simply call up a backup version. Okay, keep the atoms is the title of this next section. The preceding arguments suggest that on both practical and ethical grounds, it might be better to imagine a transporter that carries a matter stream along with the signal, just as are told the Star Trek transporters do. The problem then becomes, how do you move the atoms? The challenge turns out to be energetics, although in a somewhat more subtle way. What would be required to dematerialize something in the transporter? To answer this, we have to consider a little more carefully a simpler question. What is matter? All normal matter is made up of atoms, which are in turn made up of very dense central nuclei surrounded by a cloud of electrons. As you may recall from high school chemistry or physics, most of the volume of an atom is empty space. The region occupied by the outer electrons is about 10,000 times larger than the region occupied by the nucleus. 10,000 times larger. Why, if atoms are mostly empty space, doesn't matter just pass through other matter? The answer to this is what makes a wall solid is not the existence of the particles, but the electric fields between the particles. It's the electric fields between the particles that makes it solid. My hand is stopped from going through my desk when I slam it down, primarily because of the electric repulsion felt by the electrons in the atom in my hand due to the presence of the electrons in the atoms of the desk, and not because of the lack of available space for the electrons to move through. These electric fields not only make matter corporeal, in the sense of stopping objects from passing through one another, but they also hold the matter together. To alter this normal situation, one must therefore overcome the electric forces between atoms. Overcoming these forces will require work, which takes energy. Indeed, this is how all chemical reactions work. The configuration of individual sets of atoms and their binding to one another are altered through the exchange of energy. For example, if one injects some energy into a mixture of ammonium nitrate and fuel oil, the molecules of two materials can rearrange, and in the process, the binding energy holding the original materials can be released. This release, if fast enough, will cause a large explosion. Not telling anyone to do that, obviously. The binding energy between atoms is, however, minuscule compared with the binding energy of the particles, protons and neutrons, that make up the incredibly dense nuclei of atoms. The forces holding these particles together in a nucleus result in binding energies that are millions of times stronger than the atomic binding energies. Nuclear reactions therefore release significantly more energy than chemical reactions, which is why nuclear weapons are so powerful. Finally, the binding energy that holds together the elementary particles, called quarks, which make up the protons and neutrons themselves, is yet larger than holding together the protons and neutrons in nuclei. In fact, it is currently believed, based on all calculations we can perform with the theory describing the interactions of quarks, that it would take an infinite amount of energy to completely separate the quarks making up each proton or neutron. I'll get into quantum. Based on this argument, you might expect that breaking matter completely into quarks, its fundamental constituents, would be impossible. And it is at least at room temperature. And it is at least at room temperature. However, the same theory that describes the interaction of quarks inside protons and neutrons tells us that if we were to heat up the nuclei to about 1,000 billion degrees, about 1,000,000 times hotter than the temperature at the core of the sun, then not only will the quarks inside lose their binding energies, but at around this temperature, matter will suddenly lose almost all of its mass. Matter will turn into radiation, or, in the language of our transporter, will dematerialize. So, all you have to do to overcome the binding energy of matter at its most fundamental level, indeed at the level referred to in Star Trek Technical Manual, is to heat it up to 1,000 billion degrees. 1,000 billion degrees. In energy units, this implies providing about 10% of the rest mass of protons and neutrons in the form of heat. To heat up a sample the size of a human being to this level would require therefore about 10% of the energy needed to annihilate the material, or the energy equivalent of 100 1-megaton hydrogen bombs. One might suggest, given this daunting requirement, that the scenario I have just described is overkill. Perhaps we don't have to break down matter to the quark level. Perhaps a dematerialization at the proton and neutron level, or even the atomic level, is sufficient for the purposes of the transporter. Certainly, the energy requirements in this case would be vastly less, even if formidable. Unfortunately, hiding this problem under the rug exposes one that is more severe. For once you have the matter stream, made now of individual protons and neutrons and electrons, or perhaps whole atoms, you have to transport it, presumably at a significant fraction of the speed of light. Yes, speed of light is 186,232 miles per second, or 300,000 kilometers per second, which we cannot reach at this point yet. Now, in order to get particles like protons and neutrons to move near the speed of light, one must give them an energy comparable to their rest mass energy. This turns out to be about 10 times larger than the amount of energy required to heat up and dissolve the protons into quarks. So this turns out to be about 10 times larger than the amount of energy required to heat up and dissolve the protons into quarks. Well, even more energy than the ginormous amount of energy used to dematerialize it would you need, or would one need, or would a transporter need to actually transport them. Nevertheless, even though it takes more energy per particle to accelerate the protons to near light speed, this is still easier to accomplish than to deposit and store enough energy inside the protons for long enough to heat them up and dissolve them into quarks. This is why today we can build, albeit at great cost, enormous particle accelerators, like Fermilab's Tevatron in Batavia, Illinois, which can accelerate individual protons up to more than 99.9% of the speed of light. Wow, that is shocking. Up to more than 99.9% of the speed of light. But we have not yet managed to build an accelerator that can bombard protons with enough energy to melt them into their constituent quarks. In fact, it is one of the goals of physicists designing the next generation of large accelerators, including one device being built at Brookhaven National Laboratory on Long Island, to actually achieve this melting of matter. Yet again, I am impressed with the apt choice of terminology by Star Trek writers. The melting of protons into quarks is what we call in physics a phase transition. And lo and behold, if one scours the next generation technical manual for the name of the transporter instruments that dematerialize matter, one finds that they are called phase transition coils. So the future designers of transporters will have a choice. Either they must find an energy source that will temporarily produce a power that exceeds the total power consumed on the entire Earth today by a factor of about 10,000, in which case they could make an atomic matter stream capable of moving along with the information at near the speed of light, or they could reduce the total energy requirements by a factor of 10, and discover a way to heat up the human being instantaneously to roughly 1,000,000 times the temperature at the center of the sun. If this is the information superhighway, you better get in the fast lane. As I write this on my PowerPC based home computer, I marvel at the speed with which this technology has developed since I bought my first Macintosh a little over a decade ago. In a decade, my computer internal memory capabilities have increased by a factor of 1,000. 1,000. For doing detailed numerical calculations, I estimate that my present machine is almost 100 times faster than my first Macintosh. My office workstation is perhaps 10 times faster still, performing close to 500,000,000 instructions per second. It's 2020, I wonder where we're at now. One might wonder where all this is heading, and whether we can extrapolate the past rapid growth to the future. The point of noting the growth of computer capability in the last decade is to consider how it compares with what we would need to handle the information storage and retrieval associated with the transporter. And, of course, it doesn't come anywhere close. Let's make a simple estimate of how much information is encoded in a human body. Start with our standard estimate of 1,028 atoms. 1,028 atoms. For each atom, we first must encode its location, which requires 3 coordinates, the x, y, and z positions. Next, we would have to record the internal state of each atom, which would include things like which energy levels are occupied by its electrons, whether it is bound to a nearby atom to make up a molecule, whether the molecule is vibrating or rotating, and so forth. Let's be conservative and assume that we can encode all the relevant information in a kilobyte of data. This is roughly the amount of information on a double-spaced typewritten page. That means we would need roughly 1,028 kilobytes to store a human pattern in the pattern buffer. I remind you that this is a 1 followed by 28 zeros. Compare this to, say, the total information stored in all the books ever written. The largest libraries contain several million volumes. So let's be very generous and say that there is 1 billion different books in existence, one written for every 5 people now alive on the planet. Say each book contains the equivalent of 1,000 typewritten pages of information. Again, on the generous side, or about a megabyte. Then, all the information in the books ever written would require about 1,012, or about 1,000,000 kilobytes of storage. 1,000,000 kilobytes of storage. All the information in the books ever written would require about 1,000,000 kilobytes of storage. This is about 16 orders of magnitude, or about 1/10,000,000th of a billion, smaller than the storage capacity needed to record a single human pattern. When numbers get this large, it's difficult to comprehend the enormity of the task. It's a ginormous task. Storing this much information is, in an understatement physicists love to use, non-trivial. At present, The largest commercially available single hard disk store about 10 gigabytes, or 10,000 megabytes of information. If each disk is about 10 centimeters thick, and if we stacked all the disks currently needed to store a human pattern on the top of one another, they would reach a third of the way to the center of the galaxy, about 10,000 light years, or about 5 years travel in Enterprise at warp 9. Let me just read that again, just to take that in, process that. At present, the largest commercially available single hard disks store about 10 gigabytes, or 10,000 megabytes of information. Remember, this is in 1995. If each disk is about 10 centimeters thick, and if we stack all the disks currently needed to store a human pattern, those would be floppy disks, on top of one another, they would reach a third of the way to the center of the Milky Way galaxy, about 10,000 light years, which is distance, or about 5 years travel in the Enterprise at warp 9, warp speed, warp 9. Retrieving this information in real time is no less of a challenge. That's why getting all that information back. The fastest digital information transfer mechanisms at present can move somewhat less than about 100 megabytes per second. At this rate, it would take about 2,000 times the present age of the universe, assuming an approximate age of about 10 billion years, to write the data describing a human pattern to tape. Imagine then the dramatic tension. Kirk and McCoy have escaped the surface of the penal colony at Rura Pentha. You don't have even the age of the universe to beam them back, but rather just seconds to transfer a million, billion megabytes of information in the time it takes the jailer to aim his weapon before firing. I think the point is clear. The task dwarfs the ongoing Human Genome Project, whose purpose is to scan and record the complete human genetic code contained in microscopic strands of human DNA. This is a multi-billion-dollar endeavor, carried out over at least a decade and requiring dedicated resources in many laboratories around the world. So you might imagine that I'm mentioning it simply to add to the transporter impossibility checklist. However, while the challenge is daunting, I think this is one area that could possibly be up to snuff in the 23rd century. My optimism stems merely from extrapolating the present growth rate of computer technology, using my previous yardstick of improvement in storage and speed by a factor of 100 each decade, and dividing it by 10 to be conservative, and given that we are about 21 powers of 10 short of the mark now, one might expect that 210 years from now, which would be about 185 years from now in 2020, at the dawn of the 23rd century, we will have the computer technology on hand to meet the information transfer challenge of the transporter. Perhaps my children or my children's children will be around for that endeavor. I say this, of course, without any idea of how. It is clear that in order to be able to store in excess of 1,025 kilobytes of information, in any human-scale device, each and every atom of the device will have to be exploited as a memory site. The emerging notions of biological computers, in which molecular dynamics mimics digital logical processes, and the 1025 or so particles in a macroscopic sample, all act simultaneously, seem to me to be the most promising in this regard. I should also assume one warning. I'm not a computer scientist. My cautious optimism may therefore merely be a reflection of my ignorance. However, I take some comfort in the example of the human brain, which is light years ahead of any existing computational system in complexity and comprehensiveness. If natural selection can develop such a fine information storage and retrieval device, I believe there is still a long way we can go. The next part is that quantum stuff. I'll read that in the next video. Thank you again for your time. Hope this was interesting.